Kendra Sharp, Professor of Mechanical Engineering, and the Richard and Gretchen Evans Professor in Humanitarian Engineering at Oregon State University, being given that title for being founding and leading the drive for humanitarian engineering at Oregon State. And so as I was indicating, that need and growing educational impact in U.S. institutions, Kendra is leading that at Oregon State. Kendra is also the leader of a USAID award at Oregon State that partners with Arizona State called the Pakistan Centers for Advanced Energy Studies and Energy.
Today I'll talk about our work in at the intersection of water, energy, and climate, and particularly about the computational models that we've been developing aimed at application in data-scarce environments. So my interest is really rooted in sustainable energy, and particularly in distributed, small-scale distributed hydropower systems. And if you look at geographical regions, and you look for regions where there's the greatest overlap between need for distributed power and undeveloped natural resources, one of the areas that we find is this area up north here in the Hindu Kush Himalaya region, and in northern Pakistan in particular. So by the statistics, in Pakistan, there's an estimated 3 to 5 gigawatt shortage of power. 82 million people do not have access to energy or to electricity, and 54% of the rural population doesn't. There's an urban-rural divide, so there's more lack of access in rural areas. And they're also very familiar with hydropower because it does make up 30% of the portfolio, although largely in the large-scale systems. So estimates have put the potential for micro or mini hydropower at up to 1.1 gigawatts, but these estimates, it's very difficult to tell where these estimates came from, how they were developed, and then consequently how accurate they will be. So we set out with the goal of developing some resource maps along the lines of what you see here for solar and wind, but we wanted to do it better. We wanted to have more highly resolved resource maps, and we also wanted to be able to look at the evolution in time, thinking about the climate change impacts and how they would impact availability of the power, and in particular water. So if you think about hydropower, up here you see, you need water and you need elevation change. So you need what we call head. And to that end, in order to do this hydropower prediction or potential assessment, we needed to think about tools, developing science-based modeling tools to assess both the water availability, that was the first part, and then combine that with the elevation and with a digital elevation model to come up with our hydropower potential. So you can see our goal out here. Well, some of the challenges are that we really wanted to be able to look at this in a more highly resolved fashion than you saw on the previous maps for solar and wind. And yet, if you look at if you look at on-the-ground station data, this gives you an idea of where you have station data. This is for climate, and this is in Pakistan. Compare that, this is actually scaled. This is the density of climate stations in Oregon. So you can see there's really this data-scarce, data-sparse environment that we were dealing with. And then furthermore, we did want to look at the climate change impacts. So let me pose a couple of questions here. The first is, why are these tools useful? The second is, how do they work? And then the third is there demand? And when I talk about these tools, I'm talking about a suite of computational tools that we've developed. The first is for higher resolution climate grids. So I'll tell you a little bit about that. The second is water resource availability. And then the third is the hydropower potential. And then we built into all of these the ability to look at climate change impacts. And they build on each other. You need this one to get this one, and then you need the water resource to get the hydropower. So the water resource availability, let me start with that one. Actually, I'll back up. I'll start with the climate one. So the climate data, the currently available climate data, and the climate data, if you look into the general climate models looking into the future, is available with a resolution of 55 kilometers. So it's on a grid, and the spacing is 55 kilometers. That's not nearly high enough resolution to enable us to do these hydropower potential or water availability predictions. So the first thing that we did was to develop some downscaling tools that allowed us to take those currently existing climate models and combine them in statistical ways in order to generate these climate grids on a 1 kilometer with a 1 kilometer spacing. And these tools are available. They are open source tools that can be downloaded from our site, and you can use them over any land mass, any global land mass. So they're very widely applicable. And then we took that and we developed a hydrologic model that, in particular, it was aimed at mountainous regions that have snow. And being able to operate, a lot of hydrologic models require quite a lot of data input. So we were looking at ones that didn't require, or we were looking at developing a different type of a model that didn't require as many inputs. And this is important. I'm going to look at the Indus Basin in particular, which is up here. And if you look at this region, 50% more of the discharge, water discharge, is generated in these upper reaches. The blue here is glaciers and snow and glaciers. So 50% more is generated up there than is generated down here. So climate change impacts on this snow and glacier mass is really important. And if you think about irrigation, so we're talking about Nexus here, water, energy, and food. If you think about irrigation, 50% of the runoff that's used for the Indus irrigation scheme is from snow and glacier melt. So this part of it is very important. And then if you look at another statistic, it's been projected that because of the changes in water availability in the Indus Basin, there will be 26 million fewer people that can be fed in 2050 than 2010. So while we initially set out to look at the hydropower potential, one of the intermediate steps was to look at water availability, which has very broad application. Okay, well, what about the small hydro tool? So Nate mentioned that I'm part of a center between Arizona State, Oregon State, and universities in Pakistan. We had a visitor, and the visitor had helped us get this information about the number of small hydro plants in this very small region in Pakistan. And you can ask the question of why do we need these tools? Well, we would like to know how many micro hydro stations does it make sense to have in this region? Are they resilient to climate change? In other words, are these investments going to be lasting and useful investments if you think about 20, 30, 50 years down the road? And are they effective in meeting community needs? One of the things we've seen is that there are quite a lot of these that are not functioning right now. So that's something else we're starting to look at, the social and technical, both social and technical factors as to why they're not operating. So more accurate estimates can lead to better planning. Previously, there were these estimates of, well, maybe there's 1.1 gigawatts that's available, but it wasn't specific to any sites, it wasn't really specific to any region, and we didn't know the methodology. So we're looking at more accurate estimates that can lead to better planning. And I will say that the policy part is very important, and that's something we're looking at bringing in now. So as we move forward, we're really looking at that. Okay, in terms of how, so as I mentioned earlier, for the hydropower, you need water, information about water, and information about the mountains. This is, or the head, this is very readily available, digital elevation models anywhere in the world. It's the water part that we had to start with. So I mentioned we developed these climate grids at a finer scale, so 1 kilometer. And then we developed a hydrologic model that was appropriate for this data-scarce region, so it doesn't require nearly as many inputs as you would have for most of the hydrologic models that are used in a place like Oregon. And then we combine all these pieces, and then we're able to generate a model for hydropower potential. Now, all of these models are available on our website. They're open source and freely available. So if I think about if I envision the long-term application, this is just a preliminary result, but our long-term application is to be able to chart out this water availability, and this is, you can see that this is in flow rate, and then this is scaled in terms of a power density relative to the maximum achievable, but to come up with a map like this that shows you where it would be best to make an investment and then be able to look at that into the future. We benchmarked our model at a particular hydro spot in Oregon. This is in Falls Creek, Oregon, so it's just a little bit east of where I live. It has some common characteristics. Snow acts as a water reservoir. Snow holds the water in the winter, and we could easily make field measurements there. So we did benchmark our model at this place in Oregon. We found that it worked very well. So the last question would be, is there demand? And within 1 week of issuing a press release about our recent article in Renewable Energy, I had more than 80 requests for these tools from around the globe. And that has grown just over a period of a couple of months to, I think around 110 or so. And I have to say, I was absolutely amazed at how quickly this information traveled. And I was getting these requests within a week from Siberia and South Africa and Vietnam and just all over the place. So whether or not our tools are really science-based, in some ways research tools, so they may not be as applicable right away from the out of the box as the people who are requesting it would like. But we are moving that direction. So we want to make them more user-friendly. We've made this first step of the research tools. We're developing some case studies to help people learn how to use them. But what really surprised me in a pleasant way was to see how much demand there is for a tool like this. So this tells me that people out there are interested in knowing. So my summary here is that useful science-based tools, such as we've shown for climate, for water availability, and also for something much more applied like hydropower potential, can be developed even in these data-scarce regions. Thank you.
I would say that personally I'm driven to engineering for global development because I want to be able to use my engineering and technical expertise to have social impact. In our humanitarian engineering program or any sort of engineering for global development effort, one of the things that's really interesting is that students start to have to approach questions of ethics and really face these questions of ethics, whether those are how we work with community partners or varying safety standards internationally. These issues come up, and I think these are very important issues that we are addressing in our higher education in the US. One of the opportunities that we offer is the opportunity to be connected with community partners. This is an opportunity we offer to students. It's also a really critical opportunity for learning and learning how we work with people from very diverse backgrounds. As we know, diverse teams come up with better solutions. So this is an area where students can really practice doing that.